So we've talked about centripetal acceleration and centripetal force. We talked about the centripetal acceleration. To calculate it, we use v squared over r. And then we also talked about, for centripetal force, we have mv squared over r. Now those are good, but sometimes we may be given other variables instead of things like v. We might be given something like frequency. We might be given something like period. So what we'd like to do is we'd like to be able to actually incorporate those into our equation. And we just want to have a quick discussion with period and frequency to say like why we're allowed to incorporate that. So like for example, if I look here at this disk, I have these points A, B, and C, so they're all going to rotate around. Now, we know that when this object rotates, all three of these pieces are always going to stay in a line together, and they're going to rotate and come back to the same point in the same amount of time. Because if C ended up getting ahead of B and A was behind B, that wouldn't be good. Like all of these points will come back together after a complete rotation. Now what that means is the time it takes to go for A to do a complete circle is the same time it takes for B to do a complete circle, which is the same time it takes for C to do a complete circle. What that means is the period of rotation, regardless of where we are, is constant. If the period's constant, frequency is also constant. But this also just brings up a nice little thing. When we're talking about rotational speed, the farther out you are, the faster your rotational speed is. Because if you're at A, you only have to go this distance around in the same time that C has to go this entire distance around. So C has to cover way more ground in the same time that A has to cover this little bit. So C is going to rotate faster than A. So they'll have different rotational speeds. The further out you go, the faster your rotational speed is going to be, but they will all have the same period and the same frequency. And this principle even applies on Earth. You know, for example, somebody at the equator or in a country close to the equator, they're going to rotate and their orbital speed is going to be, nothing. It's going to be, let me rephrase that. Their speed is going to be quite quick because at the end of the day, if I have this point P, which looks like it's in Edmonton, and I have this point Q that's all out in the Pacific Ocean, in 24 hours, these 2 points are going to line up. In fact, they're going to stay lined up at all times. They have the same period. But in the time that it takes for, Edmonton to make a complete loop around, at this point here on the equator, it has to travel a much greater distance in the same amount of time. So what that tells us is that when we're at the equator, we're rotating as fast as we can, or it's the fastest possible rotation. As we move towards the poles, we're going to start to rotate slower and slower. Again, because we have less of a circumference that we have to travel. I just threw in some approximate speeds of rotation at places. So like we see Singapore being close to the equator, it's got a pretty large rotational speed. But when we look at something like Reykjavik in Iceland, Iceland's pretty far north, it's going to have a much slower rotational speed. So with that said, we'd like to incorporate those equations, we'd like to incorporate period and frequency into our equations for centripetal acceleration and force. So for us, for speed for centripetal motion, we got this v equals 2 pi r over t. Again, the 2 pi r represents our circumference. T is going to represent our period. We also know that we have v squared over r for our centripetal acceleration. So what we can do is we can take this and we can place it in there. So we're going to take that 2 pi r divided by t. We're going to square all that, so that we got to square everything, the 2, the pi, the r, and the t. So we're going to get that 4 pi squared r squared over t squared, and then we divide that by that r. So this r here is going to cancel one of these r's up here. What that leaves me with is it leaves me with this new equation for the centripetal acceleration. It's 4 pi squared r divided by t squared. So this equation for centripetal acceleration incorporates the period. This equation is on the data sheet. We know centripetal force is just mass times centripetal acceleration. So we can just take this equation, multiply it by the mass, we get the equation for centripetal force. If you happen to be given frequency instead of period, we can put in 1 over frequency because we know that period is equal to t equals 1 over f. So where I have t, we can replace it by 1 over f, and we get this equation for the centripetal acceleration is 4 pi squared rf squared. And we get this equation for Fc, this 4 pi squared r mf squared. These two equations, they're not on the data sheet, so if you need access to them, you will have to derive them. But since you get this equation with period on the data sheet for centripetal acceleration, if you're given frequency, convert that into period and then use this equation. That would be my suggestion. So this is just kind of a summary of the equations incorporating period and frequency. As mentioned though, this is the only one that's actually on the data sheet. None of the centripetal force equations are on the data sheet, and this form of the centripetal acceleration is not on there. So just be mindful of that. Always know what you're given and what you're not given. So let's finish this out. So we got a propeller on a small Cessna aircraft. It's got a diameter of 1.5 meters. So the propeller, it rotates at 50 hertz. So we'd like to find the magnitude of the centripetal acceleration at the tip of the propeller. Now, I'm given frequency. I'm going to assume I don't have these equations in front of me, except for this one, because it's on the data sheet. So because I know frequency is 50 hertz, I also can get the period from this, because that's just going to be 1 over 50. It's going to be that 0.020 seconds. Now that I have period, I have that equation for the centripetal acceleration on my data sheet with period. It's this 4 pi squared r divided by t squared. I now have the period by inverting the frequency, so I can take that and put it in here. The only thing I got to watch for, again, it's that trap. Diameter of 1.5. This is a radius of 0.75. Watch for those tricks. We like to use diameter a lot. So we're going to have this 4 pi squared. We're going to use our radius of 0.75 meters, and then we're going to divide this by our period of 0.020 seconds. And again, don't forget that square. So there's a lot of squares that you can miss. Don't forget the square on the pi as well as on the period. Really, really, really important. So for this, we're going to get about 7.4 times 10 to the 4 meters per second squared. So we could say that the magnitude of the centripetal acceleration acting on this propeller is about 7.4 times 10 to the 4 meters per second squared. Magnitude only. We're not actually dealing with direction, nor do we care about it. So what we're going to start to do next is we're going to start to look at actual motion in a horizontal circle and then eventually a vertical circle using our equations for circular motion and Newton's laws that we've already learned.